Today, we're going to continue finding antiderivatives. That is, we're going to be given a function and we want to find out what the given function is the derivative of. So we want to do our derivative process in reverse. Another word for finding antiderivatives is finding indefinite integrals. The notation is just the integral symbol without the interval from a to b. So we would just read this as the integral of f prime of x dx is equal to f of x plus c. When we write the plus c, we are writing the general antiderivative. Integration and differentiation are almost inverse operations. The reason they aren't inverse operations of each other is the plus c. When we take the derivative of any constant, we get 0. So we don't know what the constant was before we took the derivative. So when we go backwards, we just put a plus c, indicating that there was some constant here before, but we have no way of knowing what it is unless we have some additional information about the function. Just a quick note on the notation. So we know that the derivative of f of x, thinking of our derivative of f of x, if we want the derivative of f of x, we write that as f prime of x. We mean that f prime of x is the derivative of f of x. In the other direction, we could say that f of x is an antiderivative of f prime of x. So we'd say the integral of f prime of x dx is f of x plus c. A common notation when we're integrating, and we saw this in the fundamental theorem of calculus, is to write the antiderivative with a capital letter. So the derivative of capital F is f of x. So f of x is the derivative of capital F of x. That means that f of x is capital F prime of x. So this gets us to where we see this normally in the fundamental theorem of calculus. The integral of f of x dx is capital F plus c. So here we're saying that capital F is an antiderivative of f of x. So if little f is the derivative of big F is the antiderivative of little f. That's the relationship between those two. All right, yesterday we introduced a bunch of derivatives and turned them into indefinite integrals. We just want to practice that today. One of the things that we remember from derivatives is that we can differentiate by terms and we just keep constant factors. So for example, if I want to find the derivative of x squared plus x to the 5th, I can just take the derivative of each term. This is the derivative with respect to x of x squared plus the derivative with respect to x of x to the 5th. So 2x plus 5x to the 4th. We can integrate, or we can differentiate by terms. So we can also integrate by terms. If we can do, since differentiation respects addition, integration will respect addition as well. So if I wanted to integrate the function x squared plus 5x, oops, spelled x to the 5th wrong. X squared plus x to the 5th dx, I can find the integral of x squared dx plus the integral of x to the 5th dx. We can differentiate a term at a time, so we can integrate a term at a time. For the integral, instead of multiplying by the exponent and subtracting 1 from the exponent, we do inverse operations in reverse order. We add 1 to the exponent and divide by the new exponent. So we get a third x to the 3rd plus 1/6 x to the 6th. And since we're integrating, there was some constant here before. So we can integrate by terms because we can differentiate by terms. The other thing that we want to remember is that we can keep constant factors. When we differentiate, we keep constant factors. So for example, if I wanted to find the derivative of 7x to the 5th, 7 is a constant factor. So I can write this as 7 times the derivative of x to the 5th. We just keep the constant factor. So the derivative of x to the 5th is 5x to the 4th. 7 times 5 is 35x to the 4th. So we're just keeping that constant factor. If that's how it works for derivatives, that will also be how it works for integrals. So if we want to integrate 7x to the 5th dx, I can take the 7 out of the integration and say this is 7 times the integral of x to the 5th dx. The integral of x to the 5th dx is 1/6 x to the 6th plus c, and 7 times the 6th is 7/6 x to the 6th plus c. Note that I didn't have to write 7c. I just kept writing c. Since c is an arbitrary constant, if this is a +2, then this would have been a +14. Since c is an arbitrary constant, we don't have to keep track of the things that we do to c. It's just been multiplied by 7. So 7 times an arbitrary constant is just some other arbitrary constant. So if we look at it this way, we have to remember that c is an arbitrary constant. So multiplying an arbitrary constant is just another arbitrary constant. 7 times an arbitrary constant is just some other arbitrary constant. We'll look at more concrete examples of why we don't have to write 7c later on when we start taking the general antiderivative and finding specific antiderivatives. So there's a question about why I didn't write 7c here. That's because c is an arbitrary constant, and 7 times an arbitrary constant is just some other arbitrary constant. The thing that we want to note about this 7 is that it's included by multiplication. So 7 is a constant factor. So 7 is a constant factor because it's 7 times x to the 5th. Factors are things that are being multiplied. So we want to distinguish how the constant is included. In this case, the 7 is a constant factor. It's included by multiplication. And so we just keep it. We keep our constant factors. If, however, we had 7 plus x to the 5th, that's a constant term, and the derivative of a constant term is equal to 0. So for example, if instead the function was 7 plus x to the fifth, here the 7 is a constant term, and the derivative of a constant term is 0. So here it's the 7 is a constant term. It's included by addition. All right. With that in mind, we want to add a little bit to the derivatives that we saw, or the antiderivatives that we saw yesterday. So recall that we have to use the chain rule. So let's take a look at a small use of the chain rule. Remember, the chain rule is a derivative thing. So if we have, for example, the derivative of e to the 5x, the derivative of e to a thing is e to that thing times the derivative of the thing. So that 5 is the derivative of the inside. Chain rule says multiply by the derivative of the inside. That's why that 5 is there. The derivative of e to the something is e to the something times the derivative of the something. So if we translate this directly into an antiderivative statement, I could write the integral of 5e to the 5x dx is just e to the 5x plus some constant. But since we just keep our constant multiples, if I wanted the derivative of, let's say, 1/5 e to the 5x, I just keep the constant multiple of 1/5 and multiply by the derivative of e to the 5x, which is 5e to the 5x. So we just get e to the 5x. So we see that the derivative of 1/5 e to the 5x is e to the 5x. So that tells us that the integral of e to the 5x dx is 1/5 e to the 5x plus c. So the derivative of 1/5 e to the 5x is e to the 5x. So the antiderivative of e to the 5x is 1/5 e to the 5x plus c. So this leads to our small use of the chain rule. If we want the integral of e to the kx dx, where k is some constant, we get 1 over k e to the kx plus c. So there's a small use of our chain rule when the derivative of the inside is just a constant. This is a small use of the chain rule when the derivative of the inside is constant. And we can see that if we take the derivative of 1 over k e to the kx plus c, we get e to the kx. Because we just keep our constant factors. So we can modify this some more. Since the derivative of cosine, or since the derivative of sine is cosine, the integral of cosine is sine. So the integral of cosine of kx dx is going to be 1 over k times the sine of kx plus c. Applying the same thinking that we did in our e to the kx. And similarly, the integral of sine of kx dx is going to be minus 1 over k cosine of kx plus c. Remember that the derivative of sine is cosine and that the derivative of cosine is negative sine. So when we're going the other way, the integral of sine is negative cosine. The integral of cosine is sine. So, for example, if we wanted to find the integral of 5 times the sine of 3x dx. In this example, 5 is a constant multiple, and 3 is going to be the k from our equation above. So 5 is a constant multiple, or a constant factor. And the 3 is the k from the previous line. So the integral of sine of something, of sine of kx is negative cosine of kx plus c. In this case, 5 is a constant factor. It just gets carried along. The k is equal to 3, so that's what we divide by. If we want to check our answer, the derivative of negative 5/3 cosine of 3x plus c is negative 5/3 times the negative sine of 3x times 3 because of the chain rule. So if we take the derivative of our what we just found, the negative 5/3 is a constant factor, so I can hold it outside of my derivative. And I can also take the derivative of c. I can also separate by terms. So we get the -5/3 that we're just keeping. That's our constant factor. The derivative of cosine of 3x is negative sine of 3x times the derivative of the inside, which is 3. And the derivative of a constant is equal to 0. The 3's cancel out and the negatives cancel out, and that leaves us with 5 sine of 3x. Another thing that we did when we were first learning to differentiate is that if we could write terms that are powers of x, then we should write terms that are powers of x. So if we can write terms that are powers of x, then we should write terms that are powers of x. So not always, I guess. Sometimes it's going to be much worse to write terms that are powers of x. But if we can write terms that are power of x, let's try that. Then maybe we should. So for example, if we have the integral of, let's say, x squared plus 3x minus 4, and we want to, this is all being divided by an x, the x. Instead of viewing this function as a quotient, since we can write terms that are powers of x, we'll use the distributive property and divide all the terms in the numerator by x. So let's use the distributive property. So I'm going to write this as x squared over x plus 3x over x minus 4 over x. And we'll integrate these three terms dx. So we'll integrate x squared over x is just x. 3x over x is just 3. And minus 4 over x is minus 4 over x. Now I can integrate a term at a time. Notice that I'm still writing the integral symbol because we haven't done the integral thing. But now we're ready to. The integral of x to the first is 1/2 x squared. We add 1 to the exponent, divide by the new exponent. The integral of the constant 3 is 3x, so plus 3x. With 4 over x, with x to the -1, we can't add 1 to the exponent and divide by the new exponent. Otherwise, we'd end up dividing by 0, and then the math cops would come and get us. They're on high alert right now because they know we're doing integration right now. So let's be really careful. The integral of 4 over x, -4 is just a constant multiple, and the integral of 1 over x is the natural log of the absolute value of x. And then plus c because we want the general antiderivative. So using our distributive property, we were able to rewrite the function as terms that are powers of x, and that made things easy. Also in the category of writing terms that are powers of x, if, for example, we wanted to integrate, let's say, x squared plus 1 cubed, we could once again use the distributive property. So instead, we'll integrate and we'll just multiply this x squared plus 1 cubed out, or the cube of the sum of the square of x and 1. So once again, use the distributive property. So we'll have x squared to the third plus 3 times x squared squared times 1 plus 3 times x squared to the first times 1 squared plus 1 cubed dx. So 3, 2, 1, 1, 2, 3. Okay. So we got the integral of x to the sixth plus 3 times x to the fourth plus 3 times x squared plus 1. So to get the x squared plus 1, the third power of x squared plus 1, I just use the binomial expansion in Pascal's triangle. And now I have a bunch of terms that are powers of x, so I can just integrate a term at a time. Add one to the exponent and divide by the new exponent gives us a 1/7 x to the seventh plus constant multiple of 3 fifths x to the fifth plus constant multiple of 3 divided by 3 is 1 x cubed plus x plus c. If we can write powers of x, maybe we should. The other, if we can write powers of x business, has to do with x's in the denominator and square roots or radicals. So for example, if we wanted to integrate, I'm just do them both at once, the square root of x plus 1 over x to the third to x. Here, we're not using a distributive property. We're just rewriting these as powers of x. So I'm going to rewrite the square root of x as x to the 1/2 power. And I'll rewrite x, that 1 over x to the third, as x to the -3. Now I have terms that are powers of x. So I can add 1 to the exponents and divide by the new exponent. 1/2 plus 1 is 3/2. And 1 divided by 3/2 is 2/3. -3 plus 1 is -2. One divided by -2 is just the -1/2. So I'm just doing 1/2 plus 1. And -3 plus 1 is -2. Add 1 to the exponent, divide by the new exponent. You could also read 1/2 plus 1 as 1 1/2. and then convert it to a fraction by 2 times 1 plus 1. Any questions?
Yes, Professor Lich, you don't mind explain to us the binomial expression?
So
How do you-
I needed a fast way to multiply out x squared plus 1 to the third power. So if we have x squared plus 1 to the third power, that's an x squared plus 1 times another x squared plus 1 times another x squared plus 1. So if I didn't remember my binomial expansion, I would have had to multiply everything out just this way. So I get x squared, or x to the fourth, plus x squared plus another x squared plus 1. So x to the fourth plus 2x squared plus 1 times x squared plus 1. Then I have to multiply all this out again. So I get x to the sixth plus x to the fourth, and then plus 2x to the fourth plus 2x squared plus x squared plus 1. So binomial expansion is just a shortcut to finding a power of a binomial. And I happen to know the shortcut for finding the power of a binomial using Pascal's triangle, which is such a cool thing. It has its own Wikipedia entry.
Oh, okay. Thanks, Professor Lich. Thank you.
And then one of the entries in there is the binomial expansions. This by no means was Pascal's invention. It was just kind of like we just put his name on it. I don't know if he put his name on it or if we all just put his name on it, ignoring the fact that this is a very old result. And we just same with the Pythagorean theorem. By the time people started calling the Pythagorean theorem, it was an old result. It's not like this was unknown and Pythagoras discovered this. This is an old result, and then we just call it the Pythagorean theorem. Any questions? In case you're wondering, Pascal's triangle is known to predate Pascal by at least 600 years, if I recall correctly. Pascal is a 1600s dude, and this is from 1000. So check out your binomial expansion and Pascal's triangle. It is pretty cool. I guess there's kind of a habit of naming things after the wrong people. And then it leads people to think that the person for whom something is named is the discoverer of that thing. I don't know why this is true for old stuff, but not true for new stuff. No one takes the Cesar Chavez Drive exit and thinks, Cesar Chavez discovered this street in San Francisco. No one thinks that about that. But for some reason, if something is really old, like the Pythagorean theorem, we just say, oh, that must mean Pythagoras invented this or discovered it. And that's just not how it works. Humans are weird that way. Who knows? Anyway, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.
Thank you.